All right, today we're jumping into a real medical detective story. We're going to crack the case of a common but really dangerous bacterial culprit. So our case file is open, the clues are all laid out, and our mission is to unmask this mucoid monster, Klebsiella pneumoniae. Let's dive in.
So, where does any good investigation start? Well, right at the patient's bedside. We've got a pretty standard case of pneumonia, but there's this one very specific clue that just screams for attention. This thick, reddish-brown sputum that's famously described as looking like currant jelly. I know, it sounds gross, but that single piece of evidence immediately puts us on the trail of a prime suspect. So yeah, our trail really begins with the evidence from the patient, the signs and symptoms that start to paint a picture of the invader we're actually up against. So we take a look at a sample from the patient under the microscope, and whoa, the battle is already in full swing. What you're seeing here are neutrophils. They're the first responders of our immune system, and they're just swarming the area. It is crystal clear they're fighting a really aggressive infection. But what exactly are they fighting? Okay, so let's build the classic patient profile here. Our suspect often goes after people who are already a bit vulnerable, like patients dealing with alcoholism or diabetes. They come in with a severe lobar pneumonia, they've got that signature currant jelly sputum, and they're at a really high risk for life-threatening conditions like sepsis. These are the major clues you look for. All right, with our first observations noted, we follow the sample to where the real magic happens, the microbiology lab. You can think of this as our forensics unit, where a bunch of tests are going to give us the hard evidence we need to nail down our culprit's identity.
First test up is the gram stain, and boom, right away we get a huge lead. The bacteria stain pink, which tells us they're gram-negative rods or bacilli, and if you look really closely, you might notice they look kind of plump. That little detail helps us narrow down our list of suspects quite a bit.
Next, we plate the sample on something called MacConkey agar. The colonies that grow are bright pink, which confirms that our bug is a lactose fermenter. But, and this is a big but, look at the texture. See how shiny and slimy it is? Almost looks like it's dripping. That's what we call a mucoid appearance. And let me tell you, that is a massive clue. Definitely remember this visual. It's going to be super important later on. So for our third test, we use triple sugar iron agar, or TSI. The result is A over A. The whole tube is yellow. That tells us the bacteria can ferment a bunch of different sugars. We also see these cracks in the agar, and that means gas was produced. A great result, right? Well, it actually creates a bit of a problem for us. And this leads us to a classic issue in the lab, a case of mistaken identity. See, all the evidence we've gathered so far points right at our suspect, but it also points to another very, very common bacterium, E. coli. And this is the real challenge. A gram-negative lactose-fermenting rod with this exact TSI result is also the textbook profile for E. coli. So how in the world can we be sure? How do we tell our dangerous encapsulated suspect from its much more common cousin? We're going to need a few more specific tests to really break this case wide open. And here it is, the breakthrough clue. We do a motility test. Now on the left you see a positive result. That's E. coli. The growth spreads out from that initial stab line, kind of like a cloud. It's moving around. But look at the tube on the right. The growth is stuck only in that sharp line where the needle went in. Our suspect, Klebsiella, is non-motile. It can't move. Big difference. And for the final nail in the coffin, we use the citrate test. This basically asks, can the organism use citrate as its only food source? E. coli can't, so its tube stays green. But our suspect, it loves citrate. And its metabolism actually changes the pH of the medium, turning the indicator a beautiful deep blue. It's citrate positive. So, there we have it, non-motile and citrate positive. With these two definitive tests, all the doubt just vanishes. We've successfully separated our suspect from its common look-alike. The case is officially cracked. Our culprit is Klebsiella pneumoniae. So we know who did it, but now we need to understand how it does what it does. What makes this particular bug so dangerous, and what gives it that unique, slimy look? We need to take a closer look at its secret weapon. Klebsiella's secret weapon is its incredibly thick polysaccharide capsule. The best way to think about it is like a slimy, protective suit of armor. And it's this very feature that makes the bacterium such a tough opponent for our immune system. And hey, remember this picture from the MacConkey plate? That super slimy, goopy appearance? Well, that's the direct visual proof of this massive capsule. What you're literally seeing is millions of bacteria, each wearing its own suit of armor, all piled up and creating that signature look. Now, this suit of armor isn't just for show. It makes the bacteria so slippery that our immune cells can't grab onto them to eat them. That process is called phagocytosis. It also helps the bacteria evade another key immune attack called the complement system. It's really the #1 reason Klebsiella is so virulent.
Okay, now that we've identified our culprit and its secret weapon, let's put it all together in a final showdown. Think of this as the high-yield summary, a head-to-head comparison to make sure these key differences really stick in your mind.
Let's just run through the rap sheet. Motility? Positive for E. coli, but a big negative for Klebsiella. Citrate? Negative for E. coli, positive for Klebsiella. They also have opposite results for 2 other tests, MR and VP. And then there's the visual difference. E. coli colonies are pretty flat, whereas Klebsiellas are famously mucoid, all thanks to that thick capsule. These are the key distinctions that close the case every time. So, by following the clues all the way from the patient's bedside to the lab bench, we've successfully unmasked our mucoid monster. But this whole case leaves us with a final thought, doesn't it? Now that you know all of Klebsiella's tricks, you have to wonder, what other dangerous bacteria are out there, hiding in plain sight, just mimicking their more common relatives?